Hello there everyone, and welcome to today's late exam answer video. Today I'm having a look at a back titration calculation based on a request from a couple of students, but this one is quite interesting because it's in an organic context, and also we have to use some of our organic knowledge to try and figure out the ratio that we're then going to need within the back titration calculation itself. And then there's an extra added weird part of the back titration calculation as well, in terms of the percentages of the oil in Y and what we need to do with that information. So I do plan to do another back titration calculation question, be that a redox one or other, or I can do both. So again, just let me know if there's a particular question that you'd like me to have a look at, because this one is a particularly not nice one. So thank you to the students who suggested that I have a look at this. So the question is about olive oil. A sample of olive oil is mainly the unsaturated fat Y mixed with a small amount of inert impurity. Now when they say inert impurity, that's kind of important to clock, because that means that the rest of whatever makes up the olive oil is not going to react in our back titration. The structure of Y in the olive oil is shown, and then they've given us the molecular formula and the MR, which is very nice of them to do, because I wouldn't want to be counting up the number of atoms in this very long tri-ester that we have here. There is a reason why they've drawn this out, and we'll come to that in a second. The amount of Y is found by measuring how much bromine water is decolorized by a sample of the oil using the following method. So they're going to put a weighed sample of the olive oil into a 250 centimetre cube volumetric flask. They're going to make it up to the mark with an inert organic solvent. Again, inert being important, we don't want that to be reacting with the bromine water. And then we're going to titrate 25 centimetre cube samples of that olive oil solution with the bromine water, and we're using a concentration of 0.025 mole per decimetre cubed of the bromine water. They are aiming for the target titer to be 30 centimetres cubed. And in the first part of the question, we have to calculate the amount in moles of bromine in said target titer, but we also have to think about why a much smaller target titer would not be appropriate. So we'll do the potential easy bit first in terms of moles. So moles is always concentration times volume when we're thinking about solutions, is what I meant. So the concentration 0.025 times by the volume, which is 30 divided by 1,000, put it into decimeters cubed, so 0.03. So then the moles comes out as 7.5 times 10 to the minus 4. Yeah, 4. So that's one mark. And then in terms of why we wouldn't want the target titer to be much smaller, it comes down to percentage uncertainty. So we've got to recognise that when we're working out any percentage error, we do the error on the piece of equipment, which if we're thinking about a target titer would be the burette, which is plus or minus 0.15. And then we would be dividing that by our measured value, which in this case is going to be our mean titer, and then timesing that by 100. If therefore our target titer, and obviously we'd repeat it and get concordant results and then work out our mean, if our target titer was smaller, that's going to increase the percentage error, because having a smaller number as the denominator of the fraction is going to increase what value this comes out as, and thus increase our percentage error. So if we want to ever decrease percentage error, we always want to increase the size of the measured value. So a smaller target titer would not be appropriate, because the percentage error would then be too large. And why is that actually a problem? because that's saying that yes, we might work out a certain value that should be, in this case, we're thinking about a mass of olive oil, but if that comes with such a big percentage error, that means that we're essentially saying, well, it's this mass plus or minus however many grams, and a big percentage error will give us a big range in those mass values. So it might come out as like 1.5, but then if we're saying 1.5 plus or minus 0.5, then actually it could be anywhere between 1 and 2, and that's not very accurate. So having a large percentage error is not good. Okay, now on to the potentially tricky part. So we have to calculate a suitable mass of olive oil that we want to transfer into the volumetric flask up here. So the weighed sample of oil, we've got to work out what that is. We've got to use our answer to question 9.1, which is the moles of the bromine. And we are also told to assume that the olive oil contains 85% of Y by mass. So another thing to get your head around here is the difference between the olive oil and Y. So Y is this thing, Y is a component of the olive oil along with the inert impurity. So we'll come back to that. Now nicely they've given you a number of moles to use for bromine, and they will do this when obviously not being able to do part 1 will then penalise you in part 2. It's not the correct amount, so if you get any answer in part 1, use it, even if it's not correct, because you'll get error carried forwards. It's only if you can't get a number at all that I'd use the one that they've given us. Now, this is where we need to appreciate what the bromine water is going to react with in Y. So it says the bromine water is decolorised, which is a bit of a nice clue, but we need to recognise that the bromine water is going to react with all of the carbon-carbon double bonds, and that's why they've given us the sort of skeletal, mainly skeletal formula of Y, so that we can see how many carbon-carbon double bonds there are. So 1, 2, 3, 4, 5. We're going to need enough bromine water to ensure that all of those double bonds become single bonds, so that all of the bromine water gets decolorised, and we add enough for all of the double bonds to react, so that we then know how much of the olive oil we need. So we've got to establish the ratio between the, well, Y initially and the bromine water. So if the bromine water has to react with 5 double bonds, we're going to need 5 times as much bromine as we do Y. And that's the key part, and that can take some getting your head around. 1Y, because it's got 5 double bonds, will need 5 bromines to react with each of those 5 double bonds. So however you come to it, that needs to be your ratio. So if we then know the moles of bromine to be 7.5 times 10 to the minus 4 in the target titer, then we can divide that by 5 to get the moles of Y, which comes out as 1.50 times 10 to the minus 4. And then this is fairly common for a back titration. We have titrated 25 centimetre cube samples of the olive oil, which contains the Y, with this bromine. So this is the 1.50 times 10 to the minus 4. That is the number of moles in 25 centimetres cubed, because that's how much was actually titrated against the bromine, but it was initially made up to a 250 centimetre cubed solution in the volumetric flask. So we've then got to scale up the moles by timesing by 10 to figure out how many moles there would be in the whole 250 centimetres cubed in the volumetric flask. So we can times that by 10, so we times the moles by 10, and then we can figure out the mass of Y that would be present in this amount of moles because we've been given the MR up here, thank goodness. So the MR is 880, so therefore the mass of Y is 880 MR times by the number of moles, which came out as 1.32 grams. Now that is the mass of Y, not the total amount of olive oil, because the rest of the olive oil is inert. It hasn't reacted with the bromine. So we've now figured out the mass that does react with the bromine, and it tells us that we have to assume that the olive oil contains 85% of Y by mass. So this 1.32 grams is equal to 85% of the mass of the olive oil. And I'm sure those of you that do maths, funnily enough I did do maths A level, but I still have to do things pretty old school. So if I know that that's 85%, I'm dividing by 85 and timesing by 100 to figure out what 100% will be. And that will therefore be the mass of olive oil. So 1.32 divided by 85 times by 100 is 1.55. And I'm going with 3 significant figures because 3 sig fig, 3 sig fig, it could be 3 sig fig, 3 sig fig. So yeah, 3 significant figures. So to get from here to here, I have divided by 85 and then times by 100. So essentially I've worked out 1% and then scaled it up to 100%. And I'm sure, like I say, there's perhaps a better way of doing that, but that's how I would do it. So in terms of the back titration we've done here, we've had the information about the thing that we are titrating our olive oil solution against. From those moles, we've been able to then work out the moles of the Y in the olive oil using the ratio. And again, that's a very common thing we have to do in any back titration, be it redox or an acid-base one. Then we've got to think about, do we need to scale up the number of moles, and if so, by how much? Then this is where it differs slightly per question. With the moles, you can get masses if you know the MR, or you can use masses to get the MR, or you can do percentage purity, or like here, some kind of scaling of the mass that we worked out. But yeah, that's how I would go about doing this question. Hopefully all of that makes sense. Please let me know if anything that I've said is unclear. One final tip, they always give you everything in a question for a reason. So bromine water's decolorized, that is a clue. The fact that they've drawn out the skeletal part of the long kind of carboxylic acid chains as they were, they've done that for a reason. They've given us the MR for a reason, all of that kind of stuff. So if you haven't used a piece of information in the question, or you haven't thought, why have they told me that it's an inert impurity, why have they told me this, what is that volume there for, etc., that's something to contemplate. But hopefully that all makes sense. Any questions, just pop them in the comments, and any other questions you want me to have a look at, please just let me know as well. Hope you're all having the best possible weekend so far, and to those of you who have exams coming up this week, I wish you all the very best for those. Take care of yourselves, everyone.